Alright, so in this lesson we're going to start looking at spring potential energy and look at how that can help us solve problems dealing with springs. So the force applied by a spring is variable. This means in order to figure out the work done by that force, I need to figure out what the area underneath a curve of force as a function of position is. So if we look at what the force really is defined as, force is equal to k times x. Well, if x is this position, and I want to figure out the area under this curve, that area looks like 1/2 kx times x, or 1/2 kx squared. So the work done by this force is 1/2 kx squared. The potential energy for a spring is also defined as 1/2 kx squared. Now you might say, well, that's odd because the force and the direction x are in opposite directions, but since we're squaring x in here, that negative sign will actually cancel out when we do that problem. So what this allows us to do is add a new term to our equation for total energy. Total energy, originally when we talked about energy, was defined as gravitational potential energy plus kinetic energy. This allows us to add a second term of potential energy called elastic or spring potential energy. So I can define total energy of a system as 1/2 kx squared plus 1/2 m or plus mgh plus 1/2 mv squared, which means I could write my conservation of energy equation this way: 1/2 kx initial squared plus mgh initial plus 1/2 mv initial squared equals 1/2 kx final squared plus mgh final plus 1/2 mv final squared. So the thing to point out is that we can really think about springs as storing energy. This also would imply that the force due to a spring is a conservative force, which is true. So let's do a quick example problem. So I have a 1.00 times 10 to the negative second kilogram block resting on a horizontal surface. And the block is attached to an unstrained horizontal spring right here. And the spring constant is 124. I'm going to push the block this way with a velocity of 8 meters per second toward the wall. And I want to figure out what is the maximum distance the spring compresses, what is the maximum acceleration experienced by the block, and what is the period of the resulting simple harmonic motion. So first of all, what is the maximum distance compressed by the block? This is where I might want to use conservation of energy. I know m, k, and v initial. So I could say k initial plus pe initial equals ke final plus pe final. Well, the only energy I have initially is kinetic energy, since the initial distance x equals 0. It's also worth pointing out that the height of the block didn't change, and so I'm going to ignore gravitational potential energy. When the spring gets compressed the maximum amount, the kinetic energy goes to 0. All the energy has been converted to spring potential energy. So if we actually work this formula out, we can cancel out the half and get m over k, v initial squared equals x final squared, square root both sides, and I can get my x final. It's just m over k square root times v initial equals x final. To figure out the maximum acceleration of the block, well, that's going to occur when force is a maximum, so it'll occur at this maximum displacement. So ma equals kx. If I plug in what k over m is and put in my x max, which happens to be this value, that'd be my acceleration max. It happens to be a really large number for this system, 891 meters per second squared. Period of the resulting simple harmonic motion, well, if I know m and k, I could solve period. I didn't really need to do the other two. Period is 2 pi square root of m over k, so it's 0.0564 seconds. So this is a block that bounces back and forth really, really quickly, 20 times a second. And it goes 7 centimeters back and forth, moving up to 8 meters per second. So thinking about that 891 meters per second squared of acceleration makes a little bit more sense. So a couple of conceptual ideas about involving energy. If we start at what we call the equilibrium position, basically the spring is not stretched. Their potential energy would be 0, but kinetic energy would be a maximum. If this thing gets stretched out, compared with that equilibrium position, potential energy is a maximum at this maximum value of stretch. Kinetic energy is 0. And that potential energy is related to how far you've stretched it. Well, if I've released this mass, it goes to the equilibrium position. All the potential energy has been converted to kinetic energy. Well, as the spring compresses again, all the kinetic energy gets converted back to potential energy until I'm at that maximum value of compression. So if I look at an object bouncing back and forth on a spring, really what's happening is potential energy is converted to kinetic energy back to potential energy potential energy to kinetic energy back to potential energy back to kinetic energy back to potential energy, back and forth, back and forth. So let's do a second problem. And here I have a vertical spring. It's mounted to the floor, and directly above the spring, which is currently unstrained, I'm going to drop a block from rest. Collides with the spring, which is compressed to a distance of 2.5 centimeters and bringing the block to a momentary halt. Now, the reason why it's a momentary halt is that this block or this spring is compressed probably beyond the equilibrium position, and so it's going to push the block up. So from what height above the spring was the mass dropped, and how fast is the block moving the moment it impacts the spring? So the first one, we can use conservation of energy. So here's kind of a definition of what's happening. If I start with 1/2 kx initial squared mgh initial 1/2 mv initial squared, and cancel out some terms that are 0, I know h final is 0. I know x initial is 0. I know both the initial kinetic energy and final kinetic energy are 0. But I know that h final is probably, well, I could define it as 0. And so there we go. I have mgh initial, which would actually be the height above this position here, not the height h here. So we could say that h initial is really this height, h plus x final. That's because even as the block is compressing the spring, there's still gravitational potential energy being converted into, in this case, spring potential energy. So if we plug that in, we can actually calculate what h final is. And so I can calculate our h initial just by using this equation. Well, I know h initial is equal to h plus x final. So h must be h initial minus x final. So basically, the height that this is dropped above has to be related to this initial height above my 0 location here, minus how much the spring compressed. So my height that the block actually got dropped was 2.3 centimeters. The reason for that is, as this block or as this object gets dropped, it starts to compress the spring, but its potential energy in the gravitational sense is still changing. So some of this gravitational potential energy got converted to kinetic energy in the fall. The rest of it, really, we could think of it, got converted to spring potential energy as it compressed the spring. So let's answer the second question. How fast is it moving when it hit the spring? And so I could start with kind of this assumption. Initial velocity is 0. Compression of the spring, I want to know how fast is it hit just before it compresses the spring. So h final is really 0. We could say that 1/2 k f final squared, or x final squared, is 0 because it's not going to compress the spring. So I get this expression, which we can actually solve for v final like we normally would, something that's being dropped to 2.3 centimeters, and we get 0.67 meters per second as my final velocity. So I could use conservation of energy in a couple different ways. The one thing to point out is in this problem, I rearranged h to make h equals 0 this location, where in the first problem made h equals 0 that location. So we can use this conservation of energy problem even with a vertical spring to solve what's going to happen. And in fact, it's probably easier to do that than try to look at forces as this object is falling.